Definition of subsets. Let's begin our discussion on subsets. Welcome to this tutorial on subsets. Before we dive into what a subset is, let's quickly remember what a set is. In mathematics, a set is simply a well-defined collection of distinct objects. Think of it like a container holding specific things. Those things are the objects, and well-defined means we have a clear rule for what can be included in the set. We treat this collection as a single entity for the purpose of mathematical operations. Now, a subset builds upon this idea of sets. A subset is a fundamental concept within set theory, and understanding it is crucial for more advanced topics. In this tutorial, we're going to clearly define what a subset is. We won't just give you the definition, though. We'll also work through several examples to help you really grasp the concept and be able to identify subsets confidently. We'll start with the basics and gradually build your understanding, so don't worry if it seems a little abstract at first. We'll make sure you're comfortable with the idea before moving on. What is a subset? So let's move on to formally defining what a subset actually is. As we discussed on the previous slide, a subset is a fundamental idea when we're dealing with sets. Now, here's the definition. A subset is a set whose elements are all members of another set. Think of it like this: if you have a bigger group and a smaller group is entirely contained within that bigger group, the smaller group is a subset. Let me put it another way. If every single element, that is, every item in set A is also found within set B, then we say that set A is a subset of set B, so A is contained within B. Now, let's get a little more formal, just to be precise. This is where we use a bit of mathematical language. If X, that's just a variable representing any element, is an element of set A, then X must also be an element of set B for it to be considered a subset of B. What this means is, we don't allow any leftovers. Instead of that, aren't also in set B every single member of A needs to be accounted for in B. We'll really solidify this with some examples on the next few slides, so don't worry if it doesn't click completely just yet. We'll walk through some sets and see how this definition plays out in practice. Remember, the key is all the elements of the smaller set must be present in the larger set. Breaking it down. So now let's move on to a concrete example to really solidify what we've discussed about subsets. Here on the slide, we're considering two sets. The first set, labeled A, contains the elements 1 and 2. We write this as A equals an open curly brace, 1, 2, close curly brace. The second set, labeled B, contains the elements 1, 2, and 3. So, B equals an open curly brace, 1, 2, 3, close curly brace. Now, the key to understanding subsets is to carefully compare the elements. Notice that every element that is in set of that's 1 and 2 is also present in set B. Because of this, we can definitively say that A is a subset of B. Remember, for it to be a subset of B, all of A's members must also be members of B. This example perfectly illustrates that principle. We'll continue to build on this understanding with more examples in the following slides, and we'll also look at a special type of subset called a proper subset later on. But for now, make sure you understand this example. It's a foundational step in grasping the concept of subsets. Illustrative examples. Let's move on to looking at some examples to solidify our understanding of subsets. This is slide 4, and we'll be working through example 1. Here we have two sets defined. Set P and set Q. Set P, written as P equals open curly brace of B, C close curly brace, contains the elements of B and C. And set Q, written as Q equals open curly brace of B, C, D, E close curly brace, contains the elements of B, C, D, and E. Now remember from the previous slides, to determine if one set is a subset of another, we need to check if every element in the first set is also present in the second set. Let's check. Is O in Q? Yes, it is. Is B in Q? Yes, it is. And is C in Q? Yes, it is as well. Since every single element of set P, that's A, B, and C, is also found within set Q, we can confidently say that P is a subset of Q. We'll be looking at cases where this isn't true in the following examples, so pay close attention to how this works. This example demonstrates the core idea of what constitutes a subset. Illustrative examples continued. Let's move on to another example to solidify our understanding of subsets. This is example 2. Here we have two sets. Set X and set Y. Set X contains the elements 2, 4, and 6. We represent this as X equals an opening curly brace, 2, 4, 6, and a closing curly brace. Set Y contains the elements 1, 2, 3, 4, 5, and 6. So, Y equals an opening curly brace, 1, 2, 3, 4, 5, 6, and a closing curly brace. Now let's check if X is a subset of Y. Remember, for X to be a subset of Y, every element in X must also be present in Y. Let's go through the elements of X one by one. The first element in X is 2. Is 2 also in Y? Yes, it is. The next element in X is 4. Is 4 also in Y? Yes, it is. Finally, the last element in X is 6. Is 6 also in Y? Yes, it is. Since every single element of X, 2, 4, and 6, is also found within set Y, we can confidently say that X is a subset of Y. This reinforces what we discussed earlier. A subset is formed when all the members of one set are also members of another set. We'll continue looking at more examples, including some cases where sets aren't subsets, and then we'll touch upon a special type of subset called a proper subset on the next few slides. Illustrative examples continued. Let's move on to example 3. Here we have two sets. M and NM is defined as the set containing X and Y. So, M equals the set with elements X and Y. N is also defined as the set containing X and Y. So, N equals the set with elements X and Y. Now take a close look. In this particular case, both M and N contain exactly the same elements. This might seem a little strange at first, but it's perfectly valid in the world of subsets. Because every element in M is also in N, and every element in N is also in M, we can confidently say that M is a subset of N, and, importantly, N is also a subset of M. They are essentially the same set. Now, you might be wondering if there's a special name for this kind of relationship. And there is. We'll be discussing something called proper subsets in the next section, and that's where we'll clarify the difference between a regular subset and a proper subset when the sets are identical. For now, just remember that a set is always considered a subset of itself. This might seem counterintuitive, but it's a fundamental rule when dealing with subsets. Illustrative examples continued. Let's move on to our fourth example on this slide. We're now looking at sets R and S. We have set R, which contains the elements 1, 2, and 3. And set S, which contains the elements 3, 4, and 5. Now let's apply what we've learned about subsets. Remember, for a set to be a subset of another, every single element in the first set must also be found in the second set. Looking at R and S, is R a subset of S? Well, let's check. R contains 1, 2, and 3. Is 1 in S? No, it's not. Therefore, R is not a subset of S. It only takes one element missing to disqualify a set from being a subset. Now let's check the other way around. Is S a subset of R? S contains 3, 4, and 5. Is 4 in R? No, it isn't. So S is also not a subset of R. This example is important because it highlights that subset relationships aren't always automatic. Just because two sets share some elements doesn't mean one is a subset of the other. Remember, it's an all-or-nothing situation. All elements must be present. We'll build on this understanding in the next slides, where we'll discuss proper subsets and the empty set, which are closely related to this concept. So, make sure you've grasped this example before we move forward. Key takeaways. Let's recap what we've learned about subsets with these key takeaways. First, remember that a subset, by definition, contains only elements that are also found within another, larger set. Think of it like this. If you're building a smaller collection from a bigger collection, everything in your smaller collection must have originally been in the bigger one. Next, how do we actually check if one set is a subset of another? It's simple. You need to meticulously check if every single element in the first set is also present in the second set. If you find even one element in the first set that isn't in the second, then it's not a subset. We practiced this with several examples, so remember to be thorough. Now, this might seem a little strange at first, but a set is always considered a subset of itself. It might sound odd, but it's mathematically true. A set contains all of its own elements, so it automatically satisfies the condition of being a subset. Finally, let's talk about the empty set. The empty set is a special set that contains absolutely no elements. We represent it using either a symbol that looks like a curved O, which we pronounce as empty set, or with curly braces with nothing inside. This empty set is a subset of every set, even the sets that seem really complicated. This is because there are no elements in the empty set that are also in any other set. It's a bit of a mind bender, but it's a fundamental concept. Keep these points in mind as we move forward, because understanding these key takeaways will be crucial when we start looking at proper subsets and other related concepts. We'll build on this foundation, so make sure you're comfortable with these ideas before we proceed. Common mistakes. The first mistake is thinking that if two sets share any elements, then the set with fewer elements is automatically a subset of the other. That's not true. Remember, for set A to be a subset of set B, every single element in A must also be in B. Just having some elements in common isn't enough. Let's say you have a set A equals 1, 2, 3, and a set B equals 3, 4, 5. They both have 3 in common, but it is not a subset of B, because 1 and 2 aren't in B and B isn't a subset of either, because 4 and 5 aren't in A. The next mistake is simply overlooking an element when you're checking. It's easy to get caught up and quickly scan the sets, but you need to be methodical. Take your time and make sure you've accounted for every element in the potential subset. Let's move on to the final slide, which highlights some common pitfalls students often encounter when working with subsets. All right, so now we're going to talk about some common mistakes people make when figuring out if one set is a subset of another. It's really important to avoid these so you don't lose marks on a test. For example, if you're checking if set C equals 1, 2, 3 is a subset of set D equals 1, 2, 4, it's easy to see 1 and 2 are in both, but then quickly assume it's a subset without checking for 3. But 3 isn't in D, so C is not a subset of D. So, the key takeaway here is to carefully examine each element of the first set to see if it's present in the second set. Don't rush and double-check your work. If you do that, you'll be much less likely to make these common mistakes. And that brings us to the end of this tutorial on subsets. Remember, understanding subsets is a foundational concept in set theory, and it will be crucial as you move on to more advanced topics.